For the next few lectures, we will be looking at forces. We'll be going through some pretty technical stuff like Newton's 3 laws or the concept of inertia, but we really want to ease into it. So for this first lecture, we'll be going through a conceptual overview of the types of forces to clear up any misconceptions you might have had about them. It's rather chill, straightforward, so I don't foresee any problems. Get it? Foresee? Force? Yeah, that's just how we do things. Let's begin. All forces are categorized as either fundamental forces, these are contact-free, they don't require you to be touching the object for you to exert the force on it. So this is the closest thing you'd get to a Star Wars kind of force, like vroom, and then in the distance the guy just flies out. The other type of forces are the convenience forces. These are the ones that require contact. So there are 4 fundamental forces in the universe so far. And we are going to focus our attention on gravity. As for the convenience forces, it's a more intuitive, you push a chair and everything, that's something that you might experience every day. We are going to focus on the normal force, friction force, and the tension force. On to gravity first. Gravity is particularly interesting, actually. Gravity is a pulling force. Well, that's a given, because the Earth is pulling you towards the surface, and that's what's keeping you from flying up. But let me tell you something that could be a bit counterintuitive about gravity. The formula for gravity is the following. The force of gravity, subscript g, representing gravity, is equal to a gravitational constant multiplied by the mass of one object and the mass of the second object divided by the distance between the centers of the 2 objects. Now, the reason why this is counterintuitive and kind of surprising to me is because it implies that anything that has mass will exert a force of gravity on anything else that has mass in this universe. Well, that's weird, isn't it? Because that means you're attracting your computer, and your computer is attracting you at the same time. Well, it's like raw material for a pickup line. You go up to a girl and you say, "You're attracted to me because the laws of physics say so." But when you look at it carefully, this is the catch. Why you can't use that pickup line? And that is this number over here, this gravitational constant, is tiny. It's 6.67 times 10 to the power of negative 11. So whatever you have on this end, when multiplied into here, it's going to give you a tiny force of gravity that you won't even be able to feel it. But when you have the Earth under you, the Earth is massive. So one of these m's is going to be a large number. And that's going to sort of counteract the effect of the gravitational constant being so small, giving you a significant gravitational force. If you're daunted by this formula, don't worry, because most of our examples are going to be things that happen on Earth. So if things happen on Earth, the gravitational constant, well, this is anywhere, it's going to be constant. The mass of Earth is constant. And the distance between the center of the Earth to the center of any object on the surface of the Earth is pretty much constant. Like, you won't get very far, you won't get a huge difference if, say, you had a friend who was a meter taller than you, because the distance between the surface of the Earth and the center of the Earth is just so huge that extra 1 meter isn't going to make a difference. So we take all of it, and we simplify this formula into something a little more chewable. The force of gravity on Earth now, this is on Earth, hopefully you'll, this is on Earth, is equal to the mass of whatever object is on that Earth multiplied by the acceleration due to gravity. And the acceleration due to gravity, this symbol over here, is really the composite effect of all of those things in that red circle above. So everything over here just simplifies into this. And that is a constant, because it's called the gravitational acceleration constant. As long as you're on Earth, that value of the acceleration constant is 9.81 meters per second downwards. I should probably write the arrow over here to indicate that it's a vector, but you get it. I'm going to skip those arrows from now on. And this stuff over here. Okay, why is that interesting? 2 things. First, I'd like to clarify something that many lay people who are not trained in the arts of physics are not going to get. And that is the difference between weight and mass. Weight is defined as the force of gravity exerted on the object that has the mass. So that is the weight over here. Well, this over here is the mass. And weight, like any force, is measured in newtons, while mass is in kilograms. So when people ask you, what is your weight? And I hear people asking this all the time, and it's driving me nuts. And your response is, oh, I am like 50 kilograms. Well, you're actually 70, of course. But besides the point, the real answer should be, I am 700 newtons. Because that's what you asked me. You asked me for my weight, and the weight is a force. Let's shift our attention to a classic problem. What's going to happen if you dropped something heavy like a hammer and versus a feather? Are they going to fall down at a similar rate or a different rate? To the left side of the ring, we have over here the venerable Aristotle. This is Aristotle over here. And to the right side of our ring, we have our champion, the important Sir Isaac Newton. Aristotle, by the way, came way before Newton, so you gotta pardon him for what he believed in. He believed that if you drop the hammer and a feather, and this is based on intuition, the hammer is gonna fall a lot faster than the feather, because the hammer is a lot heavier. So if you believe that too, you're at least as smart as Aristotle. It's a very considerable feat. But when we look at the formula, once again, is, here's me trying to write this, Fg equals to MAG. You see that the value of the gravitational acceleration, which I gave as 9.81 meters per second squared, is going to be constant as long as you're on Earth. Or if you're on some other planet, as long as you're on the same planet, that gravitational acceleration is going to be constant for that planet. So on Earth, that's going to be 9.81 meters per second squared. Which means, despite the different mass, it's going to have the same acceleration due to gravity. So Aristotle wouldn't be too right on this one. Newton, however, is going to be right. You should look a little happier than that. Yeah, there you go. Okay. So the physics behind it is what we just mentioned. Oh, no, I'm going to have to move both of these together. But when you have the mass increasing, the acceleration due to gravity on Earth is going to stay at 9.81 meters per second squared, despite the fact that your weight has increased, your force of gravity has increased. And the two of these two, the effects of this increasing and this increasing, really just balance out in the end. Next up, we're going to be turning our attention to the convenience forces, where stuff is going to get exciting. See you then!